Good day, everyone. Today we will be continuing our lecture from the topic that was presented last meeting. If you can recall, we examined thin-walled pressure vessels as well as spherical vessels and the stresses that affect these types of bodies. You may recall we did computations on hoop stress, on circumferential stress, and part of that lecture that we haven't tackled yet is the thermal stresses. If you will look here in this illustration, this is you can observe this when you are passing some on the road, or if you are passing some bridge. There you can see some discontinuities in the road, and you may wonder why is that. So that is the reason for that is related to our lesson for today about thermal stresses. As you know, materials, when heated or when there is a change in temperature, there's also an associated change in its dimensions or in its length. That's why we need this type of discontinuities for our steel materials in building their bridges. Because if there will be a change in temperature, let's say an increase, the normal thing that will happen is the body will expand as explained here. And if it's a fixed body and it expands and it has no room to expand, then a stress will be developed. Let's investigate how we can compute that stress with the concepts that we have already discussed. Let's just look at this here. Let me just read this, and I've mentioned it earlier also that a change in temperature can cause a body to change dimensions. The general rule is if temperature increases, the body will expand, and if the temperature decreases, the body will contract or shorten. And we have an equation here that that shows us the relationship of the elongation to the change in length. If you will recall, we um, have this delta for elongation, and this one here is elongation due to thermal changes in temperature, and this is an empirical equation that is equal to alpha. This is delta T, or the change in temperature from this is final temperature minus initial temperature and multiplied by the length. Here are our givens. So alpha is referred to as the linear coefficient of thermal expansion, and the units for this one is per temperature unit, or you have 1 over degree Fahrenheit. For the FPS system, you have 1 over degree Celsius or 1 over Kelvin in the SI system. We have a table at the back of our reference material for this values, to determine these values. And delta T is the algebraic change in temperature of the member, that is final temperature minus initial temperature. Length is the original length of the member, and this delta T would be our elongation, or the algebraic change in the length of the member. I think I have given some introduction about this. If you will go here to this picture, look at this picture. This is a pipe system, and you can see that there are bends. I recall I have explained before that these bends is to compensate for any dimension change or length change due to changes in temperature. Again, these materials, when subjected to changes in temperature, might change their dimension also. So if they are fixed, these materials will be subjected to stresses that may affect their integrity in the long run. So time will come, if the material can't handle the stress anymore, it might rupture, or it might break, and it will fail to deliver the function for what it was designed for. So that's why we need to design our design our these materials properly, and take account of all the stresses that these materials may be subjected to. So for statically determinate members, the change in the length can is direct substitution. You can easily calculate it from this given equation if you have all the variables. But for statically indeterminate members, the change in length produces a thermal stress that we can compute from the what we can compute from the force and given the area. So it's still a type of stress. So their equation will still be F over A. So that is for statically determinate members. It's straightforward. You can substitute to this equation. But for statically indeterminate members, there will be additional steps. But we will be using techniques that we have already studied earlier. Let's have this example here. The material is A36 steel, and before we start this, we'll be looking at the back cover for the coefficient of thermal expansion for this type of steel, A36. So this is an A36 steel bar shown, and it is constrained to just fit between two fixed supports. And the initial temperature, T sub 1, is 60 degree Fahrenheit. If the temperature is raised to T sub 2, 120 degree Fahrenheit, or double, we are to determine the average normal stress developed in this bar. We will be needing our previous knowledge about stresses and strains, elongations, and our new knowledge and our new equation here about thermal stress to answer this problem. Let us first determine our givens. So for your given, you need to draw your free body diagram, and it's pretty much this illustration right here in the side. Let's just do that one. So if we isolate this body from its environment, remember this is a constraint and it's fixed. You have here force A and a force B, which are both unknowns. There's no given, there's no data about these forces. So what we need to do is we need to solve for the force that results from the expansion of this material due to the change in temperature. We have our given temperature, initial 60 degree Fahrenheit, and the final temperature is double of that, 120 degree Fahrenheit. We already have a hint of what we should be doing. As I've mentioned earlier, we'll still be applying our previous knowledge about stresses and strain, our equations, the PLEA, that knowledge to be applied here in computing the thermal stress. We are looking for the average normal stress. If you can recall from our equations, there is no stress there in our equation, even for, let me first write down the equations that we will be needing. If you can recall, the elongation would be equal to PL over EA, and our new equation now is the elongation due to thermal stress is equal to the alpha, or the linear coefficient of thermal expansion, the change in temperature, and the length. So L, let me write, L is 2 feet, and the area is 0.5 by 0.5 square inch. Now let's analyze this member right here. Since the problem states that this just fits right here, all right, so there is no room for elongation. It's exactly fitting between point A and B, but there is a change in temperature. Therefore, a force will be generated because this material would like to, since the temperature increase, this material will expand, and because there is no space here for it to expand, or here, a stress is generated, and that stress is due to a force that is developed, an internal force that is developed in the member. All right, now let's put it into numbers. Let's write down that the let me go up. Let's write down that the elongation for A to B should be equal to 0. And that elongation, let me write it again. That elongation should be equal to 0, and that would be the elongation due to our thermal expansion. This is the summation of the elongation, okay? So there is an expected elongation due to thermal expansion, but since there is no room, it is opposed by an elongation due to a force that is in the in here, or in here. All right, and these forces will be opposite. So let's put a minus sign there. So the elongation due to the expansion of the material due to the increase in temperature will be countered by an elongation due to a force because of the constraints, and that elongation would be equal to 0. So let's write down, let's further transform this equation, that our elongation due to thermal expansion would be equal to the elongation due to the opposing force, and we will be using both these equations right here. Let's substitute these values here. So you have alpha, delta t, L, all of which are given, right? Alpha, we can look it up from our from the back cover of our book. Let's give a value to alpha. So alpha, if you will check the back cover of our book, for A36 steel, it's given as 6.6 times 10 to the negative 6 per degree Fahrenheit. So since we are in the FPS system, we'll be looking for our in the column of the FPS system, there's also a corresponding value for SI. Let's finish our equation now. So this would be equal to P L over EA. And what are we looking for in this equation? So our alpha can be taken from the table, delta T can be computed, length is given, E. We can also look at the tables given in our book for this is Young's modulus for steel, which we can again take from the tables. A we can compute, L is common, and what we're looking for is P, or the force. Since we are looking for a stress, we have an area but we don't know the value of the force. We will be solving for this. So let's transform this equation in terms of the given variables. Therefore, the L would be cancelled, yeah. There are L in both sides. Therefore, our P would just be equal to EA will be transposed. We have the coefficient of linear expansion, the change in temperature, and the Young's modulus multiplied by the area. This would be the equation you'll use. And since all the variables here are given or can be looked up in tables, we can directly solve for P. And let's do a direct substitution. We found that the coefficient of linear thermal expansion is 6.6 times 10 to the negative 6 per degree Fahrenheit. And the change in temperature is T2 minus T1, or 120 degree Fahrenheit minus 60 degree Fahrenheit. And the modulus of elasticity for steel is, we have 29, or yeah, alright, we have 29 times 10 to the 6th pounds per square inch. So we're in the FPS system. And the area, we have 0.5 times 0.5 square inches. So let's input that in our calculator, and we will find that the P would be equal to, let's have a consistency of units first. So we have here the degree Fahrenheit will be cancelled, the square inch will be cancelled, therefore we will be getting pound force for our unit. So just multiply all of this here, and we will get 2,871 pounds, or 2.871 kips, or KIP, kilopounds. We are looking for the stress, and the stress, we know, we'll have an equation of stress will be equal to P over A. If we will substitute further, our equation, stress would be equal to 2,871 pound force all over 0.5 by 0.5 square inch PSI. If you input that in your calculator, you will get 11.5 kilopound per square inch, or KSI. Now, therefore, our final answer, let's write it down. Answer, our stress that is asked initially. So determine the average normal stress developed in this bar due to the 2.871 kilopounds that is developed due to the constraint, and we have 11.5 KSI, kilopounds per square inches. Okay, so that's how you solve statically indeterminate problems when there are neither given values for each force. Okay, let's have another example. Let me read the problem here. We have a rigid beam shown in this figure, and it is fixed to the top of three posts. As shown here, you have steel on the sides and an aluminum post in the middle. It's made of A992 steel and 2014-T6 aluminum. The post in each the posts each have a length of 250 millimeters when no load is applied to the beam, and the temperature is 20 degrees Celsius. We are to determine the force developed or supported by each post if the bar is subjected to the shown uniform distributed load of 150 kilonewton per meter of length, and the temperature is raised to 80 degrees Celsius. First, let's take a look of the properties that we will be needing. So what are those? You need your coefficient of thermal expansion, the alpha, and you also need your Young's modulus or modulus of elasticity for A922 steel and 214-T6 aluminum. Let me make a table here on the side. Um, it better be a bigger table. One is A992 steel and 2014 T6 aluminum. What we need is the alpha value and the modulus of elasticity value. You will find these tables in the back cover of our reference material. We are operating in SI units, so what we need is this table you can see here. We are looking for aluminum 214T6. The modulus of elasticity is 73.1 gigapascal. Let me write that down. 73. Oops, sorry. 73.1 gigapascal. And what else do we need? Coefficient of thermal expansion, the last column. It's 23 times 10 to the negative 6 per degree Celsius. 23 times 10 to the negative 6 per degree Celsius. Next is for A992 steel we have here. So the modulus of elasticity is 200 gigapascal and the coefficient of thermal expansion is 12. We have 12 times 10 to the 6 degrees Celsius and 200 gigapascal. Alright, so let's also write this down as our given. Okay. So this is our data from our tables. And let's fill out the rest of the given. We have your T1 20 degrees Celsius. You have T2 final temperature 80 degrees Celsius. Basically, you need to draw the free body diagram. It's actually here, but better that we draw another. Alright, and then you have your 3 posts. Let's remove the post. Let's have the free body diagram only. Alright, so there will be a force developed for each of the posts. Let's write it down. Let's call them as, this is force in steel, this is force in aluminum, right? The aluminum is the middle one, and the right side is also force in steel. Let's resolve this. As you can see, we have a uniform distributed load, the shape of which is a rectangle. So if you have distributed loads such as this, you can resolve it as a single force here. You know that this is 300 plus 300 millimeters. Therefore, this is 600 millimeters, or 0.6 of a meter, multiplied by the distributed load equation is, or sorry, the value is 150 kilonewton per meter. Therefore, this can be resolved into 150 kilonewton times 0.6. That would be 90 kilo newton still. Alright, we have here a known variable, 90 kilonewton. This is the, let's analyze this first. This is the free body diagram, and the posts are not rigid, they are deformable. The only rigid one here would be the beam, as stated in the problem. Therefore, there will be no deformations for the beam. Our concern for the deformations or the elongations would be in the posts. Now, therefore, we need to solve for the forces for which these posts are subjected to. And to do that, we need to have a force balance. But first, let's follow our system, and let's write our required first. So what is the problem asking us? Determine the force supported by each post if the bar is subjected to this variables here. Now, we will be looking for force in the steel posts and force in the aluminum post. Let's go to our solution. Now, we have already drawn the free body diagram, but we don't have any value for this, for the forces. Let's do a force summation. Summation forces y positive going up is equal to 0. 0 is equal to all the forces going up, or force in steel, there's 2 of that, so 2 times the force in steel plus the force in aluminum is also going up, and opposed by 90 kilonewton, that's going down. Okay, so do we have any anything that we can solve here? We still have 2 unknowns. So now what we know is that twice the force in steel, let me put that in red, twice the force in steel plus the force in aluminum will be equal to 90 kilonewton, and let's label that as our equation 1. Now, how do we solve this if we have two unknowns? We need another set of equations, and we can get that set of equations from our strain or our elongation equations. Let's take a look at the diagram first. Now, as mentioned in the problem, the temperature is increased to 80 degrees Celsius. Therefore, these materials will have a corresponding increase in their lengths due to thermal expansion. And another thing is the load is applied to the beam, therefore compressing the posts. So there is another component of the elongation, but it is compressive, therefore it tends to shorten the member. Now let's write down our equation for that. So for steel, let's write steel first. For the steel, the total elongation, let's call it that, will be equal to the elongation due to thermal expansion, which is delta sub t, and that would be minus the, or plus the elongation, which is negative, due to the force, which is st. We can also write the same for the aluminum. Elongation of the aluminum would be equal to the thermal expansion plus, or plus negative the, because it is compressed, right? When you apply this this force here, distributed force, the beam is compressed, therefore it exerts a force to the each post that tends to shorten them. That's why we have a negative sign for the elongation. And we have equations for this elongation for thermal and for the elongation, which is PL over EA. Let me write that down again. This is PL over EA, and this would be the coefficient of thermal expansion, the change in temperature, and the length. Now we just need to manipulate our equation here. Okay, let's also establish that due to the distributed load, due to the same geometry, and due to symmetry, the elongation in the steel would be equal to the elongation in the aluminum. So these two would just be equal to each other, and we can substitute these equations here to this equation that we developed due to symmetry, that the elongation for the steel would just be equal to the elongation in the aluminum. Now let's substitute our values. By the way, what else we don't know? Oh, right. Alright, so the diameters, so these are cylindrical posts. So the diameter is, for the steel post, are 40 millimeters, and for the aluminum post is 60 millimeters. We need to compute for the area, and they are uniform. They are similar in their length, which is 250 millimeters. Let me add another blank page. Now let's substitute our values of our coefficient of thermal expansion times length plus the PL over EA for aluminum and steel, which are equal to each other as we determine here. The elongation for steel would just be equal to the elongation in the aluminum, and we will substitute all of this. Let me write down the general equation before we plug in our values. So the coefficient of thermal expansion of steel, the change in temperature, the length plus the force in steel times the length all over the Young's modulus of steel, which we have already read from the tables, and the other side is for aluminum. The same thing, but the subscripts would be different. Okay. Alright, that was quick. Now we plug in all our known values. For steel, the coefficient of thermal expansion is 12. 12 by 10 to the negative 6 per degree Celsius multiplied by the change in temperature, that would be 80 degrees Celsius minus 20 degrees Celsius. So we can remove this from the equation. Multiplied by our length, which is 250 millimeters. We want to operate with meter, so let's convert this. This is 1 meter is 1,000 millimeter. Therefore, this is 0.25 meters. Cancel that meter. Plus the force in steel is unknown. All right, let's just put it there. Let's do a color coding. So this is an unknown, so it's in red. Multiplied by this is 0.25. We already did that conversion, so let's just write it. 25 meter all over. The for steel it's 200 gigapascal. This is 200. How much is giga? That's 10 to the 9th. Gigapascal, that would be Newton per meter squared. And multiplied by the area, which is circular. So this is pi multiplied by the diameter is given, so that's pi over 4, and d squared, that would be how much for steel? Alright, 40 millimeters. 40 millimeters converted to meter. 1 meter, 1,000 millimeter. This is square, so you square the numerator and the denominator, both the units. This is also squared, so 40 millimeters squared. Pi d squared over 4. Eraser. Okay, this will be cancelled, and you will be left with meter squared for that. So let's plug in that in the calculator later. Let's continue with our equation on the other side. The next one is for aluminum. Aluminum is coefficient of thermal expansion 23 times 10 to the negative 6 per degree Celsius. The same change in temperature is 60 degrees Celsius. You can cancel that unit. The length is the same. Let's write it down as 25 meters, 0.25 meters, I'm sorry. Plus, also in red because it's unknown, the force in the aluminum multiplied by the total length all over, what's the coefficient of thermal expansion? Sorry, the Young's modulus, 73.1 gigapascal. We have 73.1 times 10 to the 9th Newton per meter squared, multiplied by the area, pi over 4, and this is a different diameter, so 60 millimeters squared, multiplied by our conversion factor. Let me erase that first. Alright. Millimeter, and this is squared. Alright, now all you need to do is to plug all these values and input it in your calculator, and we will be, since we still have two unknowns, we will just be generating another equation, and let's write it in red, and we will get our equation 3. Let's solve it in terms of the force in steel. If you input that, the force in steel, you'll find out would be equal to 1.216 of the force in aluminum minus 165.9 times 10 cube, so kilo. And this is our equation 2. If you can recall, we have an equation 1 earlier, this one here. So if we can solve this equation simultaneously, we will eventually get a value for our force in steel and our force in aluminum. Now let's transpose this side here to the other side. But first, let's examine the consistency for our units. Here you have meters squared. Okay, so the degree Celsius is cancelled, the millimeter is cancelled. You have meter here left. This is Newton. Newton, you can cancel Newton from the force. Alright. So the area can also be cancelled. Newton can be cancelled because you also have a Newton here for the force. Right? So it's cancelled. Alright, so what remains is meter, or a unit of length, which is, because these equations are about elongation, so practically they have units of length. Now let's manipulate this equation. Right here we have force in steel minus or better, let's transfer the force in steel. Okay, so 1.216 the force in aluminum minus the force in steel. I just transpose this in here, and let's transpose the 1 with the value on the other side, so it becomes positive. That's 65.9 times 10 cubed. And our equation 1 is 2 twice force in steel plus force in aluminum equals 90 kilonewton. So the force in aluminum plus twice the force in steel equals 90 times 10 cubed, right? It's also in kilo. So let's solve this equation. If you can recall your algebra, so what do you want to do? For me, I will multiply this by 2. and then I will do elimination so that I can eliminate this 2F steel here. Therefore, let's add this. Therefore, this will be 2.216 of FAL. Oh, sorry. I need to multiply that first. Sorry. So 1.216 times 2, that would be 2. What would be 2.4 and 32 plus 1. So that would be 3.432 FAL. Since this is twice, so it will be eliminated, right? And we can solve for our force in uh, force in uh, in aluminum, since we've eliminated the force in steel. Therefore, 2 times 165.9 331.8 plus 90. Remember, they are both should be multiplied by 10 cube. Now we can solve for aluminum since we already eliminated the uh, force in steel. And if you follow this, 331.8 plus 90 times 10 to the times 10 cube and divided by 3.432, we get that the force in the aluminum is 122,902.0979, and this would be in newtons. Or force in aluminum is equal to 123 22.902 kilo newton. If we can go back to our equation 1, that we can substitute this value, that twice of the force in steel plus the force in aluminum is equal to 90 kilonewton. We can transpose it to the other side. The force in steel therefore is equal to 122.902 kilonewton negative plus 90 kilonewton divided by 2. So 122 kilonewton minus negative 122.9 kilonewton plus 90 kilonewton divided by 2, which gives us the force in steel equals 16,451.04895 newtons, or 16.45 kilo newton negative. That's negative. We now have a negative value for our force in steel. Therefore, what we need to do, look at the force in aluminum, it's positive, meaning our assumption from our free body diagram is correct. But for steel, it's negative. Therefore, we go back to this free body diagram, and we correct the sense. Let me just erase that and draw a new one. All right. So the force in steel is a negative 16 kilonewton. That's why we reverse this. Now let's extend our analogy for the beams. For the post. If you look at this free body diagram is for the beam, right? And if we apply our law of action and reaction for each beam, there should be an opposite and equal reaction, right? So using that analogy, we can see that the steel is in tension. Look, because the direction of the force is reversed, right? According to our calculations. And if you will if you will analyze each beam and apply the third law, this force will have a reaction of opposite and equal magnitude. Same goes for the aluminum. As you can see here, the middle, and the reaction should be opposite and equal in magnitude. Therefore, the steel, the steel posts are in tension, as you can see here. This is in tension. This steel is also in tension, and the aluminum is in compression. Alright, so that's the analogy. We will not base the sense just because of the sign of our answer here. The force in aluminum is positive, the force in steel is negative. But if you will extend your analogy, you can conclude that the steel, based on this free body diagram extension that we did, that the steel is in tension, both steel posts, and the aluminum is in compression. So another analogy for that is take a look at the coefficients of thermal expansion of each. Which one has a higher coefficient of thermal expansion? Of course, 23 is higher than 12. Therefore, the aluminum post will expand more than the steel posts. That's why it will feel compressed here, right? It will feel the aluminum post will feel compressed because it expands, or the elongation is more than that of the steel. So that's another analogy, and also the math proves it if we extend our analogy of our free body diagram. Okay, so this free body diagram originally that we drew is a free body diagram for the beam, right? So any external forces here that we want to apply to the post, we need another and separate free body diagrams, and we apply the Newton's third law. Alright, I hope that is clear, so that we can proceed to another problem. Let me read. Here we have a 2014 T6 aluminum tube, and its cross-sectional area is 600 millimeters squared, and it is used as a sleeve. So the sleeve is aluminum, and the bolt is an 836 steel bolt, and the cross-sectional area is 400 square millimeter. So the initial temperature is 15 degrees Celsius. So when the temperature is 15 degrees Celsius, the nut holds the assembly in a snug position such that the axial force in the bolt is negligible. If the temperature increases to 80 degrees Celsius, T sub 2, determine the force in the bolt and the sleeve. Now let's write our givens. What do we know? Our given are the cross-sectional area of the aluminum. It's already an area, alright? So that's 600 square millimeter. Cross-sectional area for the steel bolt is 400 square millimeter. Temperature 1, T sub 1, 15 degrees Celsius. The final temperature is 80 degrees Celsius. What else do we need to know? Alright, let's construct the table. The table that I did earlier. Alright. So I have a line here, another line. Let me write. This is for A36 steel, and this is for 2014 T6 aluminum. We can just copy the, again, look there, but we have the data for aluminum. That's 23 times 10 to the 6th and 73.1 gigapascal. Let me write that down first. You have 23 10 to the negative 6 per degree Celsius, and that's how much again? 73.1 gigapascal. 73.1 GPa. Let's look for A36 steel SI units. A36, the modulus of elasticity is the same, 200 gigapascal, and the coefficient of thermal expansion is also same, 12. So we have 12, 10 to the negative 6 per degree Celsius, and we have a 200 gigapascal. Alright, so let's determine what is required by the problem. We are asked to compute for the force in the bolt, which is steel bolt, and the force in the sleeve, or sleeve, which is an aluminum sleeve. Now let's extend our free body diagram by cutting a cross section here. Alright, let's expose that one. We have this head of the bolt, and then alright, I will do a freehand. And remember, there is a bolt inside. Let's compare their coefficient of linear expansion, linear coefficient of thermal expansion, and evidently the aluminum will have a higher coefficient. Therefore, the aluminum will expand more than the steel bolt. So what will happen if as you can see here, there is the head of the bolt. There's this part here that will constrain the elongation of the aluminum, even if it will elongate more, and the bolt will elongate less than the aluminum. So imagine what will happen to the sleeve if the bolt is not elongating at the same length or at the same rate as it. So the sleeve will be compressed, right? So think about that. The bolt inside doesn't elongate at a rate the same to the sleeve, and you have this part here. So this sleeve wants to elongate, yeah, but it is constrained because the bolt is slow to elongate, or they are not the same. They don't have the same rate. Therefore, your sleeve will be in compression. Let's draw this. So the sleeve is in compression. This is your force of the sleeve in aluminum. Okay, I will omit this part, but this is, and the force in the bolt would be in tension. Okay, so since the temperature will be increased, there will also be thermal expansion for each material, and we can write that if we do a force summation, that Fs should be equal to Fb, and this is how we do an analogy so that we can establish which the sense. And as a result of our analogy, we assign that the force in the sleeve is a compressive force, and the force in the bolt is a tensile force. So now that is our first equation. But what else? Should there only be uh, elongation due to the change in temperature? Of course not, because as you can see, they have a different coefficient of thermal expansion. That's why forces are generated between them. The other material, the elongation is longer, and the other material, the elongation is shorter relatively. Therefore, there is also an elongation or a strain that is due to the generated force. So if you can see, the application here would be the same as for the previous problem. We will still be needing the equations that we learned earlier. That is your elongation due to the force, that's PL over EA, and the elongation due to thermal changes, this is your alpha delta T L. Now we did our analogy, we determined our variables and the values. Let's plug in, or let's generate um, our equations for the elongation. So for the elongation in the sleeve, what are the components of the elongation in the sleeve? So the elongation in the sleeve due to thermal expansion, right? Let's call this sub in the sleeve, okay, and T. And the other component is the due to the compressive force, Fs, plus, so since it's compressing, we write it as negative or shortening. It's also an elongation for the sleeve, but due to the force, Fs. And let's substitute that to this equation. So Fs, all of this is equal to this. Fs equals to Fb. And the other side is for the elongation of the bolt due to the temperature, plus the elongation due to the Fb, due to the force. And it's positive because we predetermined that it is in tension. Alright, so therefore this is our general equation where we plug in our values. Okay, Now let's go to plugging in our values for due to the thermal expansion of the sleeve, which is aluminum. We have 23. Now we're just going to plug it into the equation. Multiplied by the change in temperature, that would be 80 minus 15, that's 65. Alright, let's write it. 80 degrees Celsius minus 15 degrees Celsius. And do we have the length? Oh, okay, actually we can cancel the length. Is there a length given? Oh yeah, the length is given. Oh, alright. Let's not cancel it. The length, I'm sorry, we didn't emphasize it, but the length is shown here. As you can see, it's 150 millimeters, or 0.15 meter. Let's multiply that. 150 millimeter multiplied by 1 meter per 1,000 millimeters plus, this is a negative value, so let's write negative, minus, due to the force, that is your PL over EA. Let's substitute P with Fs. So Fs multiplied by the length, which is, let's write it down as 0.15 meters at this side, all over the area is given. E for steel is 70, for aluminum is 20.1 times 10 to the 9 Newton per meter squared, multiplied by the area of aluminum is 600 millimeter squared. We need to convert that into meter. So this is 1000 meters squared. I hope you can still see it, so that we can cancel out the millimeter. So that is for the left side, and we have an equal sign here. Later on, let's plug it in later on our calculator. So for the side of the bolt, which is a steel bolt, 12, that's the alpha is 12 times 10 to the negative 6 per degree Celsius, multiplied by this 80 minus 15, that's 65 degrees Celsius. So we can cancel that unit. Let's cancel the units. Multiplied by 0.15 meter. So meter remains, minus for the force side, that's FB, unknown as well, multiplied by the same length, 0.15 meters, all over, for aluminum, that's 200 gigapascal. 200 times 10 to the 9 Newton per meter squared, multiplied by the area is cross-sectional area 400 millimeters squared. To convert, multiplied by 1 meter over 1000 millimeter, but also squared. So remember, if you square the numerator, you also need to square the denominator in your calculator. Alright, so all these equations will give us, we can substitute, since we go back to equation 1, we know that Fs is equal to Fb. Therefore, this is an equation with only one unknown. We can substitute either Fs here in Fb, or you can substitute Fb here in Fs, since they're just the same value. They're just equal. So if we input all of this in our equation, our final answer that we get would be, for final answer, we established earlier that they are equal, right? So the final answer would be Fs is equal to Fb, and that would be equal to, our answer would be 20.3 kilo Newton. Okay, now we have answered our our required since we established that they are equal. If you want to read more about this topic, just check out our reference material written here. And for some additional readings, you can also check the other two books that are shown here from Mechanics of Materials and Strength of Materials. That's all for this lecture. Your activity will be posted um, to follow. So please study this material before answering your activity. Thank you for your time and be safe, everyone.